Okay, so question 12 says that the following op-amp, it has a finite open loop gain given by A, and for this op-amp, the closed loop gain is given in this equation here. So the question asks us to solve that this equation is true. So in other words, it tells us that we have this op-amp circuit in the non-inverting configuration, and it tells us that in this circuit here, the op-amp is having a finite value for A, and when you solve it, you get this equation for the closed loop gain here, and it asks us to verify that this is true. So a couple things to point out is that previously we knew about the case in the so when there's an ideal op-amp, ideally the open loop gain A should be infinity in an ideal case. And then if you solve this circuit for the ideal case, where if open loop gain is infinity, you will arrive at that equation here. But now we're told that this op-amp is different. It's no longer the ideal case. It has a finite value for A, and we need to solve this circuit here. So let's just, before we start, let's look at the op-amp in the open loop configuration. So you've got your output of V out, and then you've got your two inputs, V minus and V plus. And we know that how the op-amp works is that it takes V out, and then it is equal to open loop gain A multiplied by the difference of the two input terminals. So it would be V plus minus V minus. So we're going to use this equation in a moment. I just write it down there and save it. Now in the case of the op-amp circuit we're solving, we know that in the ideal case there is no current that is supposed to be going into the input terminals of the op-amp. So on this feedback side of the op-amp, we see that there is a single current path that goes from V out, passes through R2, then we take that voltage, call it V minus, and then we pass the current through R1, then reach the ground. So you can identify a voltage divider. So a voltage divider here, and the voltage divider says, okay, well, you've got your sample point that exists in between the two resistors in series, which is the sample point is V minus is equal to V out multiplied by, well, in the numerator it is the lower resistor, and in the denominator is the summation of the series path of the two resistors. So this is just voltage divider formula. Now, so what we do now is we can take this equation that we solve for V minus, and we can input into the previous equation we discussed for the how op-amp behaves in open loop configuration. So now we combine these two equations, we get V out is equal to A times V plus, and then minus everything in the V minus. So it's V out multiplied by R1 division R1 plus R2. And then there's one more thing. In the circuit that we're solving here, in this circuit, we see that we put the V in is plugged into the non-inverting terminal V plus. So we substitute V in for the V plus. So V out is equal to A times V in minus V out R1 over R1 plus R2. Okay, so now let's do a distribution of this A term here. So that becomes A times V in minus A times V out times R1 divided by R1 plus R2. Okay. So let's do let's do some consolidation of terms and get this equation into a form that we can extract V out divided by V in, which is equal to closed loop gain G. So the first step is okay, let me write it more clearly. So V out is equal to here. So now let's move this term addition to the left side. So now it becomes V out, okay, plus A times V out times R1 divided by R1 plus R2. This is equal to A times V in. Okay, and well, I can factor out the V out now, so it becomes V out multiplied by 1 plus A times R1 divided by R1 plus R2. It's equal to A times V in. Now I will divide both sides by V in. So now we have a V out divided by V in multiplied by 1 plus A times R1 divided by R1 plus R2. This is equal to A. And then divide both sides by this parentheses term. So V out divided by V in is equal to A divided by 1 plus A times R1 divided by R1 plus R2. Yeah, so this is equal to G. This is equal to G. So let's call that rather G. And we just need some little bit more manipulation to get this into the form that we want, looking like this right here. Okay, so first of all, let's divide both the numerator and denominator divided by A. So what we see now is G is equal to, closed loop gain is equal to, divide both the numerator and denominator divided by A, which is equal to 1 over A plus R1 divided by R1 plus R2. So now the next thing, let's do this. Let's multiply both the numerator and denominator by this R1 plus R2 term. So, okay, so this is multiply R1 plus R2, and this is also multiply R1 plus R2. So numerator and denominator. Okay, so by doing that, we get the R1 plus R2 divided by R1 plus R2 multiplied by the denominator. And the reason why I do this is so that R1 plus R2, okay, is because now it will cancel out on the second term in the denominator. So it's R1 plus R2 divided by A, but then it cancels out for the second term, so it just becomes the R1 is left. Yeah, so So, actually, one thing I can also do is separate the denominator a little bit more. So, numerator r1 plus r2 divided by r1 divided by a plus r2 divided by a plus r1. So there's a common term here. R1, R1, R1 appears 3 times. So let's divide both the numerator and the denominator divided by R1. So then you do that, you get R1 plus R2 divided by R1. Then now let's divide denominator by R1. R1 divided by A plus R2 divided by A plus R1. So now becomes, the numerator becomes R1 divided by R1 is just 1 plus R2 divided by R1. So it becomes 1 plus R2 divided by R1. For the denominator, let's distribute out the R1 term. So for the first term here, it's just 1 divided by A, because the R1 cancels. For the second term is R2 divided by R1A. And then for the third term, the R1 also cancels, so plus 1. So now the numerator is in the form we want, but the denominator needs a little bit of change. So okay, so we have the 1 plus already here. We have that here. It's just the second part that's a little bit different, and the numerator is identical. So now let's do this. Well, actually, it will be more clear if I first just rearrange the denominator. So that will be 1 plus R2 over R1. The numerator stays the same. I'm just going to rearrange the addition here to group the two A's together. So it's a 1 plus, and then 1 over A plus R2 over R1A. Let's put that in the parentheses. So now we can see we can distribute out the 1 divided by A. So now it's same as the numerator. Now let's distribute out the 1 divided by A. So now it's 1 plus R2 over R1. Yeah, and this is the final answer. Well, I guess let's just rewrite this a little bit. 1 plus R2 over R1. The whole thing division by 1 plus 1 plus R2 divided by R1 divided by A. And this is in matching with here now. So question 12b is a continuation of the previous problem. So in the previous problem, we are told that the op-amp this time no longer has that ideal case of infinite open loop gain. It is A for the op-amp, and as a result, we calculated the equation to solve for the closed loop gain, which is V out divided by Vn, and we found it was this equations here. So now the question set now provides us with two resistor values for R1 and R2, and it says that please find the percent deviation E of the closed loop gain G from the ideal value of the ideal case compared to the reality case for the following open loop gain of 10 to the third, 10 to the fourth, and 10 to the fifth. So in other words, in the past, we assumed the op-amp was a ideal op-amp where the open loop gain is infinity, and when you made that assumption, the closed loop gain was this equations here. But now we are told that now we have a finite value for 10 to the third, 10 to the fourth, 10 to the fifth in this open loop gain. So now we have to use these equations to solve for the closed loop gain. And the question asks, compare the reality case against the ideal case, and what percent deviation are we talking about? And we call that by E. So in the first case, let's first actually solve for the ideal case when open loop gain A is infinity. And that equation is 1 plus R2 divided by R1, which is 1 plus R2 is 9 kilo ohms, and R1 is 1 kilo ohms. And clearly the kilo ohms cancel off. This becomes This becomes 1 plus 9 is 10. The units is volts divided by volts. So this is the ideal case. It's 10 to the 10 volts divided by volts. We want to compare the reality case against this. Okay, so case 1. Let's kind of draw some so we don't confuse. Okay, so case 1 is when A is 10 to the third. Now let's solve for G. Let's call this G of 10 to the third case, and we use this equation here. So it's 1 plus. Now R2 divided by R1 we're given are the resistor values, so it's 9 divided by 1. Kilo ohms cancel off, and then denominator is 1 plus 9 divided by 1 divided by A, which is the 10 to the third case, like this. So it's a 10 divided by 1 plus 10 divided by 10 to the third. And now I will plug this into the calculator. And so this is equal to, well, it's equal to 9.9 with some zeros and then like some more 9, but just cut it off at 9.9. And the question asks, so if it's 9.9, what is the percent deviation from the ideal case? Oh, units is volts divided by volts. So what is the percent deviation? So how we do that is we do reality divided by ideal. And why we put the ideal in the denominator is because we're comparing to that. So whatever value you're comparing to, you put that in the denominator. Our reference value goes in the numerator, so that will be reality divided by ideal. And so the reality value is 9.9 and the ideal value is 10. So this is equal to 99%. So 99% is 1% away from the perfect, 100%. So the percent deviation E in the 10 to the third case, it is 1% away from 1% away from the ideal. It's 1% too low, so negative 1%. So we solved for the 10 to the third case. Now let's move on to the 10 to the fourth case. So A is 10 to the fourth. Okay, same thing. We're just going to plug it back into these equations here. So the 10 to the fourth case. Okay, it's going to be the same resistor value, so I'm just going to copy this. With one modification. Now we're looking at the 10 to the fourth case. So this is equal to 10 divided by 1 plus 10 divided by 10 to the fourth. So let me just plug this to the calculator, which is equal to 9.99. Okay, now so reality divided by ideal, which is 9.99 divided by 10. So what percent is this? So okay, this is equal to 99.9. There's 3 nines, so 99.9%. So we can infer from that that the the E percent deviation in the 10 to the fourth case is 0.1% lower than the perfect 100%. Okay, so finally, let's solve for 10 to the fifth case. So 10 to the fifth case, I solved this from the before, so let me just ignore that from okay, yeah, so 10 to the fifth case. So one more thing is, you notice that instead of solving it, we can just do some pattern recognition. So we saw that when a is 10 to the third, it's minus 1%. When a is 10 to the fourth, it's minus 0.1%. So you can infer that if a is 10 to the fifth, through pattern recognition, we can see that the 10 to the fifth case should then be negative 0.01% deviation. And I'm doing this because I don't want to solve it again. So, okay, so these are our final answer for the problem. But before I comment, I just want to say one more comment. It is that the purpose of this exercise was to demonstrate this thing, this notion that the ideal approximation is actually, which assumes that open loop gain is infinity. The ideal assumption actually is a very good measure of the behavior of the circuit, and the reason is because even when a is 10 to the third, which is not infinity, but even when a is 10 to the third, you're only minus 1% error. And then when a is 10 to the fourth, you're only 0.1% error. And then when a is 10 to the fifth, you're only 0.01% error. So you're practically at the correct answer. So this is why we don't actually need to use the reality equation. That's just extra unnecessary work. The ideal approximation is a very suitable representation for the behavior of the circuit. So this is why we almost always assume the op-amp is ideal. So now for part C, which is just a continuation of the previous problem. So I will copy the circuit over. So it says, the question says that given that V in is 1 volt, so we apply 1 volt here for each case being those these three cases of the open loop gain. So these are the 3 cases. So for each of these 3 cases, it says to find the voltage difference of the input voltage terminals. In other words, find the voltage that is this voltage minus this voltage, V plus minus V minus. First of all, we need to, in order to solve this, we need to consider that the equation for the closed loop gain in the non-ideal case, which we solved that in part A. So let me copy this equation here. So we had solved this in part A, and this is the voltage that is V out divided by V in. That's the definition of closed loop gain G. And ideally, we would have the op-amp where the open loop gain A in the op-amp would be infinity, but in the real life case, A is finite, not infinity, it's finite. And so in that case, we have to use this closed loop gain equation here. And the question is asking 3 different cases of open loop gain, 10 to the third, 10 to the fourth, and 10 to the fifth. Okay, so first of all, we're told that V in is 1 volt. So this V in is 1 volt here. So in which case we can actually plug in. So G is V out divided by V in. V in is 1 volt. And then we plug into this closed loop gain equation the resistor values provided in part B. So R1 is 1 kilo ohms and R2 is 9 kilo ohms. So in which case we plug in. So we have like 9 kilo ohms divided by 1 kilo ohms. And then we have the denominator is 1 plus 9 kilo ohms divided by 1 kilo ohms divided by A. So I just plug into this equation here. Let's solve for that. So now the gain, which is equal to V out divided by 1, well, then that's just a V out, is equal to 1 plus, now the kilo ohms cancel, so it becomes 1 plus 9, which is total is 10 in the numerator. The denominator becomes 1 plus, and then 1 plus 9 is 10 divided by A. So this is the equation for the V out. So I will save this equation and I will use it in a little bit. Now the question asks to solve for what is V plus minus V minus. So we need to find out what is this V minus voltage. For that we can observe there's a voltage divider. So we can see that we apply voltage at V out. It passes the current through this R2 resistor, and then the middle point is the V minus. There is another path through the second resistor, and then it goes to ground. In that case, we can observe that because that, okay, so there is, in the ideal op-amp, you have no current goes into the input terminals of the op-amp. So in that case, we have a voltage divider. This is a valid path of voltage divider through this here. So we can observe a voltage divider where V minus voltage is equal to the input of voltage divider. And if you recall the formula for voltage divider, you put the lower resistor in the numerator, and then in the denominator you use the summation of the two resistors in series. So now let's plug in the resistor values, which is given in the part B was 1 kilo ohms and 9 kilo ohms. So it becomes 1 kilo ohms divided by 1 kilo ohms plus 9 kilo ohms. So now we see V minus is equal to V out multiplication. The kilo ohms cancel, so it's 1 divided by 10. So I will save this equation. Okay, let's see here. So we also can now plug in this V out that we solved to this equation in V minus. So now V minus is characterized by 10 divided by 1 plus 10 divided by open loop gain A multiplied by 1 divided by 10. Now you can see that the 10 cancels. So what we are left with is v minus is equal to 1 divided by 1 plus 10 divided by open loop gain A. Okay. Now the question asks for what is the voltage difference, V plus minus V minus, what is this voltage difference here. So let's call that VD is equal to V plus minus V minus. Now we know that V plus is connected to V in. You see that this V plus is V in. So VD is equal to V in minus V minus, which is this we just solved. So then it's 1 divided by 1 plus 10 divided by open loop gain A. So this is the equation that we will be using. Now the question says that for each of the three cases, so A of 10 to the third, 10 to the fourth, and 10 to the fifth. So let's just plug in A for here. Actually, let's recall that we're told that in this problem V in is 1 volt, so I'm just going to substitute 1 minus 1 divided by 1 plus 10 divided by A. Let's use this equation. Okay, so we're just plugging in 3 different values for A and finding the result. Okay, so case 1 is when open loop gain is 10 to the third. Yes, so so we just solve for this. VD, let's call this VD of 10 to the third case. This is equal to 1 minus 1 divided by 1 plus 10 divided by 10 to the third. Okay, so 10 to the third is 1000, so it's 1000 divided by 1000, so that's 1. And then the second one is 10 divided by 1000. So this is 1 minus 1 divided by so 1010 divided by 1000. Now you can see that there is a double divide by 1000. So double divide by 1000 is the same thing as multiply the numerator by 1000. So this is 1 minus 1000 divided by 1010. And then you can see that that one of the zeros cancel, so then becomes 1 minus 100 divided by 101. Then this is equal to 101 divided by 101 minus 100 over 101. So you can see this is 1 over 101. I was hoping not to use calculator, but we need to use calculator. So let me go plug this to the calculator. So this is 9.9 times 10 to the... There's some more decimal points, but that's sufficient. So this is equal to 9.9 millivolts. Okay, likewise, we repeat the problem for the case 2, which is when open loop gain A is 10 to the fourth. So we plug in this. So 1 minus 1 divided by 1 plus 10 divided by 10 to the fourth. I'm plugging into here these equations. So yeah, it's the same process. So it's 1 minus 1 divided by, so it's 10,010 divided by 10,000 Yeah. So then this is equal to 1 minus 10,000 divided by 10,010. So then that, okay, so 10,010 divided by 10,010 minus 10,000 divided by 10,010. This is to make the numerator, the denominator the same, so we can perform subtraction. Then it becomes 10 divided by 10,010, which is equal to 1 divided by 1,001. So yeah, we still need calculator for this. So VD in the 10 to the 4th case is equal to 1 divided by 1001. So let me quickly plug this to the calculator. It becomes a so 0.999 times 10 to negative 3. So VD in the 10 to the 4th case is equal to 0.999 millivolts. Okay, so now case 3, which is the open loop gain A of 10 to the 5th case. Is it, 10 to the 5th case? Yeah, 10 to the 5th. So okay, to avoid the need to solve all the problems meticulously, we can just do some pattern recognition. So when A was 10 to the 3rd, it was 9.9 millivolts. And then when A was 10 to the 4th, we add an extra digit of 9, but then we divide the whole thing by 10. So can we infer that through pattern recognition, can we infer that VD of 10 to the 5th, recall the pattern is each time is dividing by additional 10, so now 0.09, and then we add one more digit of 9, so 19999, and then millivolts. So the pattern that I'm describing is, here is 9.9 millivolts, divide by 10, add one digit of 9, becomes 0.999 millivolts, and then divide by 10, add one more digit of 9 is 0.09999. Okay, so this is the final answer for these 3 cases. The point of this exercise was to demonstrate the degenerative feedback, where when it's an ideal op amp, that there's a virtual short circuit going from the V minus to the V plus, so that the 2 input terminals are virtually shorted. They have the same voltage because of this infinite open loop gain A being infinite in the ideal case. That said, because we are dealing with the real op amp, now we cannot make that assumption, so we have lost the virtual short circuit approximation. We have lost this virtual short circuit here. Yet we have demonstrated that even with a non-infinity open loop gain of even 10 to the 5th, which is not an infinity, but even that is still very close to 0. I mean, 0.0999 millivolts is relatively close to 0. So we can say that even you don't have the ideal op amp, but the virtual short circuit assumption is still a close enough approximation. It still works. It's a close enough approximation to solve the op amp. So this is the final answer.